All right, what is up everyone? This is Dev Oski from the BTQ development team, and I'm going to show you some of the progress that we've been making on our quantum safe version of Bitcoin called BTQ. So a few things I'm going to show you. I'm going to show you the creation of a brand new wallet, signing messages with that wallet, generating addresses for that wallet. I'm going to show you mining coins into that wallet, getting the unspent outputs that belong to that wallet, creating transactions around that, and signing those transactions. So as you can tell, there's quite a lot to go through since the last video, and we've been making great progress. So first of all, one of the things that we really care about at BTQ is providing the users of BTQ, who are also probably the users of Bitcoin, with all of the technologies that they are familiar with, such as the Bitcoin CLI. We have our own version of that called the BTQ CLI. And that's what I'm going to be using to invoke some of these commands. So in the left-hand side terminal, I have my BTQ node running. So the BTQ chain is there waiting for commands. In the real world scenario, there would be lots of people running this software together, forming a network, and that would be the decentralized network effect. But for now, this is just my local node of BTQ, and I'm running on the regression testnet, which means that blocks are free from the perspective of proof of work, and that's useful because I'm going to be mining a bunch of blocks, getting some coins, and then creating transactions out of those. So you can consider this to be like a completely fresh blockchain with only the Genesis block and no other blocks. So what I'm going to do is I'm going to do a command here. You can see down at the very bottom, BTQ CLI create wallet. So I'm creating a brand new wallet, and I'm calling it the Dilithium wallet. And you can see that it's spit out an object here with the name of Dilithium wallet. So now I have a Dilithium wallet. I need to get an address for it. So let's first just have let me do another command here, which is called get wallet info, and you'll be able to see some information about this wallet. For example, the balance is 0, there's no unconfirmed balance, there's no immature balance from new blocks being mined and new coins that have not yet reached maturity. The transaction count is 0. It's a brand new wallet, so that's some information about that. So now I can do this next command, which is called get new Dilithium address. If you're familiar with Bitcoin CLI, you might know get new address. Well, this is getting an address using the Dilithium cryptographic algorithm, which is a quantum secure algorithm. And so this is the first kind of hint towards the fact that this is a quantum secure protocol and the upgrades to the Bitcoin protocol from the perspective of quantum security. So we're using Dilithium as our cryptographic algorithm there. And so now we have this new address beginning with the letter R that kind of loosely resembles a Bitcoin address, but we're using this new Dilithium improved cryptographic security algorithm here. So now that I have this address, I'm going to do another function and another CLI command, which is called sign message with Dilithium. So I'm going to use the same cryptographic algorithm again to sign an arbitrary message, and then after that we're going to basically verify that that message signature was indeed correct, and hence prove that the most basic cryptographic primitive of the Bitcoin protocol, which is the ability to sign and verify messages, is now satisfied, but in a cryptographically secure way against the quantum threat, you could say. So I'm going to do the classic computer science message, which is hello world, and we're going to get this wallet address to sign hello world for us and create a Dilithium based signature. So instead of ECDSA, we're now, or SHA-256, we're using Dilithium, and this is a quantum safe signature. So now what we can do is we can actually verify that this signature is indeed correct and that we're able to cryptographically securely sign any arbitrary message. So what we'll do is we'll take the message, which was hello world, and once again we'll need the address to kind of verify that signature against, which is this address. And then what we need to do is copy paste that entire signature, starting from here. Paste that in, and now we're performing that, basically computationally inexpensive way of verifying a very computationally expensive to break cryptographic signature. And so we're able to solve that, prove that signature is valid in very small computational time, but the amount of compute that it would take to break this signature now, even when quantum computers become sort of the meta, is still impractical and provides that amazing cryptographic security. So you can see at the bottom here it says true, which means that signature verification is true. And just for the sake of the point, what I'll do is I'll come into this signature now and I'll deliberately make it invalid. So I'll take this letter B here that kind of is here living at the bottom. Not sure if you can see that. Delete that B and I'll change it to an A. And so now when I run that signature verification function, we're now not able to validate that signature because the signature is now invalid. And so instead of it being true and we have a valid signature verification, it's now false. So you can see that the most important kind of premise that underlies the Bitcoin protocol is the ability to cryptographically hash messages such that it would be very, very difficult to guess the conditions under which that cryptographic hash was created, but you can verify the address and we can verify the signature in very little computational time. And that's what we've proven here. So now what we can do is we can generate some blocks. What I'm going to do is mine some blocks, 101 blocks. And the reason I'm mining 101 blocks is because blocks are, like the coins that you get for mining blocks, are immature and unspendable for the first 100 blocks. The reason for that is that you don't want to mine some blocks and then spend them, and then the block that you mined becomes orphaned and the coins that you spent became invalid. That's part of something called the double spending problem. You need the block to mature, as in live long enough such that there are more blocks ahead of it, and you can feel certain that those blocks are not all going to be orphaned simultaneously, and then orphan your blocks and invalidate your coins. So 100 is the amount of blocks that the Bitcoin network has decided is sufficient. When we launch this chain, we might change the number of blocks, particularly in the early days, when the hash rate is low, because for security reasons, if someone with a lot of hash rate came into the network, they might potentially be able to undo some of the blocks if they could prove that they have a blockchain with a greater chain height. And so you need a certain amount of blocks, maybe it's 100, maybe it's 1,000, we'll test that and make sure we come up with the correct number. So now we've generated 101 blocks. We should have one block that gave us coins that has maturity and therefore has an output that this wallet can spend. So what I'll do is I'll now type another command, which is called list unspent, and that's going to list all of the unspent outputs that this wallet has, which should be the coins from one block, because we mined 101 blocks, and 100 is the amount of time it takes for them to become mature. So we should have one block that's mature and one output that we can spend. So let's list unspent, and we can see here now that we have an array of one object, which is this transaction, and we have an amount of 50 BTQ coins. And we're able to spend that particular output. So what we'll do is create a transaction, a raw transaction. Let me copy this command. And then what we'll do is we'll get this transaction ID here, and we'll say we want to spend this output. We want to spend the 0th output here. E out 0, E out 0. And then we'll say, okay, what address do we want to send these coins to? Well, let's just send them to ourselves, because we only have one wallet on this entire network. So if we send them to ourselves, that's what we want. What have I done here? I've missed one of a quote. There we go. So now we have this serialized raw transaction that is not yet signed. So this information here is the actual serialized data that would appear in a block on the blockchain. Not in humanly readable form like this, it's kind of transformed into the kind of next level down in the protocol. And so what we'll do now is we'll do the next command, which is sign transaction with dilithium. And again, we're using this quantum safe dilithium hashing algorithm, and we will sign with this algorithm. So I'll put the hex here, and then it will add all the signatures in serialized form to this raw transaction. And you can see there that this transaction has now been signed with the dilithium algorithm. And if we were connected to the broader BTQ network with a bunch of people, we would then broadcast this transaction, and it would get mined in the next block, and then it would become part of the next block and part of the network, and be immutable and last forever. So that has been the demonstration of all the progress that we've been making with integrating dilithium quantum safe cryptographic algorithms into the BTQ core source code. As you can see, all of the functionality is now there to have a fully functioning network where you can create a wallet, spin up new wallet addresses, start mining, and send coins to people. So yeah, if you've been following along, stay tuned for the next set of additions that we will be doing. A lot of testing to be done, and then hopefully we'll be spinning up a block explorer and publishing the testnet of this blockchain live. Everyone can get a wallet, start mining, send transactions to each other, and start testing it, and we'll just go from there. So thank you so much for watching.